Once again, I welcome you to another series of our online classes. And today we'll continue looking at, or we continue from where we ended. Last time we were looking at chemical bondings, and today we're looking at the shapes of the molecules. So, chemical bonding will give you molecules. Now, what we'll discuss today is that we would want to see on how the molecules will be shaped. And to explain this, we use a theory normally called as valence shell electron pair repulsion theory. So this concept is basically based on the valence shell electron pairs repulsions. Okay, from what we've discussed, using the Lewis structure, we were able to draw the structure of we were able to draw the molecules. Now, the thing that remains there is that how are the molecules shaped, or what will be the geometry of that molecule? To help us understand or predict the shapes of the molecule, basically we will use a phenomenon, a theory normally called as the valence shell electron pair repulsion. So from the Lewis structure, there are two things that we established. In a molecule, there are two types of pairs. There is what you normally call as the bond pair. There is what you normally call as the bond pair, and there's what you normally call as the lone pair. So now, this theory or this concept use these two types of pairs to predict the shape of the molecule. Now, a few things to highlight before you determine the structure of the molecule is that this theory is based on the valence electrons. So the theory only concerned with the valence electrons. Then it only looks at the electrons in the molecule to be paired, and those pairs are distributed in the molecule. Then the pair of electrons are repelled. So there is repulsion between the lone pair of electrons, and that repulsion has to be minimized for the molecule to be stable. So note, using this phenomenon, the double bond and the triple bond are considered in the same way as the single bond are considered. So the theory will apply the Lewis structures if two or more resonance structures can be drawn from the molecule. Then formal charges are not shown on the Lewis structure. So now, what we do? First thing first is we first draw the skeleton structure of the molecule. If you want to determine what the shape is, we first draw the structure of the molecule. Then, from the structure of the molecule, we determine the electron pairs on the central atom and distribute them equally to minimize electron repulsion. Then after we do that, then we can describe the geometry of the compound or the molecule. For example, let's look at aluminium, right? Aluminium is able to form three bonds. If you have, let's say, aluminium, is 1, 2, and 3. Now the question is that using the repulsion theory, how will these three pairs be distributed? Now you see, this looks like a T, but ideally, for these to be equally repelled, what you get is that it will assume the shape that looks like this, which is normally called as a triagonal planar. In a triagonal planar, this bond angle will be 120, 120, 120. So meaning all the lone pairs are equally repelled, and in so doing, they will assume a shape that is triagonal. It will not look like a T like this. No, but you have aluminium in the center, and equally the bonds are distributed like that. So it's the same thing that you get if you have 3 pairs. Note that there are no lone pairs here. So since there are no lone pairs in here, it will only have a shape that looks like that. So using this theory, the electron-pair repulsion theory, there are 2 things that we consider. The first thing is we consider the lone pairs, and we also consider the bond pairs. Then note that each of these are pairs, so meaning each of these has 2 electrons. So we consider the lone pair and the bond pair. So we look at the molecule. We first assess the molecule and see if that molecule has no lone pairs. In this example, there are no lone pairs, there are only bond pairs. Then in some instance, we also look at if the molecule basically has lone pairs. And I'm sure as we proceed and look at more examples, we'll get to understand what we are talking about. Okay, this gives you a table with examples, and each examples it gives you what the expected shape would be, what the bond angle will be, and how the molecule will look like. Now note that all the bond pair are repelled equally. So bond pairs are repelled equally. So these are the bond pairs. If the molecule has 2 bond pairs, the shape will be linear. If the molecule has 3 bond pairs, the shape will be triagonal planar with 120 degrees bond angle, 180 degrees for a linear bond angle. So for example, this molecule will be like this, 180. The second one will be like this, so be 120, 120, 120. The third one has 4, so meaning it's a tetrahedral. Tetra means 4. The bond angle will be 109.5, and this is how it will look like. It will look like this. Now check, it doesn't look like, for example, it will look like this. Now when drawing a tetrahedral, we have to be very careful. If you draw something like so, here the bond angle is 90, so this is not a tetrahedral. With a tetrahedral, we have to draw it in such a way that we have this, then we have something like this. So that gives you how a tetrahedral will basically look like. Then if the molecule has 5 bond pairs, you expect it to be trigonal by pyramidal, meaning 90 degrees and 120. If the molecule is octahedral, it has 6 lone pairs, it will be an octahedral and it will have 90 degrees bond angle. So this table will help you understand what the expected shape of the molecule will be based on the number of bond pairs that are there. Second example, we have this molecule, methane. It's a tetrahedral, 109 bond angle. Then this is also a tetrahedral. We'll get to understand those in details as we proceed. Then we have this molecule is linear. I'm avoiding talking about this now. We'll talk about them as we continue. This molecule is a trigonal planar. Let's start with beryllium chloride as our example. Now, you note we first draw the central atom. So we have beryllium chloride. Like I've said, the one that is low in numbers is the central atom. So in this case, you have 1 and 2. So beryllium will be in the center. So we first draw beryllium with 2 electrons. Beryllium is in group 2, the valence electrons is 2. So you have this will be beryllium. Then you add the chloride. So you have this would be chloride and this would be the chloride. So this is the chloride and the chloride. So chloride would be 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So this is how the structure of the molecule will look like. So the second step that we need to get is that we need to determine how many bond pairs are there. So when we look at the molecule, there is this bond pair here and this bond pair. So meaning in terms of bond pairs, it equals to 2. Lone pairs, there is 0. So this tells you that the molecule is actually linear with 180 degrees bond angle. So what you get from what we've established is the molecule is linear and 180 degrees bond angle. And this is the bond angle that you have there. Second example, we look at aluminium chloride. Now, aluminium chloride, the chemical formula is LC3. Of course, from what we've established, we know that aluminium will be in the center. So aluminium will be like this. Now, aluminium is in group 3, so meaning it has 3 valence electrons. So you have 1, 2, 3. Then we draw the chlorides. So you have a chloride there, a chloride over here, and a chloride over there. So you have a chloride, chloride, and a chloride. Now, with the chloride, each one of them has 7 electrons as valence electrons. So you have 1, 2, 3, 4, 5, 6, 7. Same applies here of 1, 2, 3, 4, 5, 6, 7. Same applies here of 2, 1, 2, 3, 4, 5, 6, 7. So the second step that we do is we count the pair, the bond pairs. So we have one bond pair here, we have a bond pair here, we have a bond pair here. Now, when you look at a bond pair is a pair of electrons that exist between two atoms, meaning the electrons that are being shared between two atoms. So if you look at this, these are not being shared, so they are not bond pairs. But if you look at 1, 2, 3, they are being shared with other atoms. So these are actually bond pairs. So now, since if you look at the bond pairs, will be 3, lone pairs will be 0. So what would be the expected shape? The expected shape will be a triagonal planar. What would be the bond angle? The bond angle will be 120 degrees as your bond angle. So this is what you get. Triagonal planar, 120 degrees, 3 bond pairs, 0 lone pair, and this would be a shape of aluminium chloride. Okay, let's look at one last example before we go to the next one. Let's talk about methane. Now, methane is CH4. Of course, carbon is a central atom, so we can draw carbon. We have 1, 2, 3, 4. Then now we have hydrogens. 1, 2, 3, 4. So there's 1 here, 1 there, 1 there, and 1 there. That's H, 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 H. So looking at the lone pair, this has 1, 2, 3, 4. So in terms of bond pairs, in terms of bond pairs to be bond pairs equals to 4. Lone pairs is equals to 0. Since it has 4 bond pairs, what will be the shape? The shape will be a tetrahedral, and the bond angle will be 109.5, like that. So in drawing, now, if you have 4 bond pairs, there is you can actually make a mistake by drawing this like this, where you have 90 degrees. This will be wrong. It's a tetrahedral, it has to assume the shape of a tetrahedral. Now, in trying to draw a tetrahedral, I know it to be a bit difficult, but in simple terms, you can draw it like you have carbon in the center, then you have one, then there, this, and basically that. You can draw it in a proper way, but just to assume a tetrahedral. Now, looking at the example, this is how a tetrahedral will look like. It will look like something like this. So when drawing tetra meaning 4, don't run into a mistake of drawing a 90 degrees bond angle. No, it has to be 109.5 bond angle. So with what we've discussed, I think on this lecture, I can end here. Then I'll continue in the next video talking about more examples using the repulsions theory. Thank you very much.